So in this video, we're going to execute the analysis or the different types of analysis in the reinforced concrete frame that we previously built in another video. If you haven't watched the video with the definition of the model, I advise you to have a look at that video first. I am also going to be making reference to older videos in which we used a steel moment resisting frame. So in case there is something that you don't know and it's not explicitly explained here, just have a look in those initial 4 videos in which you might have the answer. So the first thing that I want you to notice here, I'm doing the gravity analysis. And in the gravity analysis, in the recorder for the gravity reactions, that is actually what I care about the analysis. I mean, there are different types of recorders, as you know. There are for the elements or for the nodes. In this case, I'm just interested in getting the reactions. So in order to do so, I have to define for what nodes I want to do it. In this case, I just changed, or I adapted the nodes to be the ones in the base, A, B, C, and D in the base. And then for the degrees of freedom, as you might remember, this is a 3D model. So I have to do it for the degrees of freedom that I care. The first 3 are the displacement, or they are linked to the displacement in the 3 global directions, while the last 3 are related to the rotation in the 3 global directions as well. So basically, these are going to be forces, and these are going to be moments. I am just getting all of them out, just because I want to know everything. And then everything else is pretty much the same as it was in the steel moment resisting frame. So if you have a question or you want to go a little bit more in depth with all these parameters, just go and have a look there. So this is for the gravity analysis. So I have created also a small script in order to just assemble my analysis that is called run gravity. In this small script, I am just basically sourcing the model itself, or the construction of the model, and I am sourcing the analysis. And that's it. It's going to assemble it. So when I call, or when I use the OpenSees script, the OpenSees window, I can just call directly to these 2 sources by calling only one of them. So I'm basically going to do it now. So I'm going to just write here in the OpenSees, and this is the folder that I'm using for my model. I'm going to write source run gravity.tcl. I press enter, and then it's telling me that the gravity analysis has started and actually just finished, and it's going to give me my recorders that I indicated to record. So in this case, if I open my recorders, you will notice that I have this here that I normally copy to Excel, and this is probably the manual way to do it. There are probably more automized ways to do it with, I don't know, Python or MATLAB, or even the OpenSees itself, or the TCL code itself. So what I'm going to do is I'm going to just import it to Excel. And as you remember, these ones here, or this last row, is the one that I care about. So I have displacement in X, displacement in Y, forces in global X, forces in global Y, forces in global Z, or in this case, reactions. So that's why I get positive. It's going upwards because it's a reaction. Same thing for the 3 moments. All of this is for the first node. And then these ones here are for the second node. These ones here are for the third node. And these ones here are for the 4th node. So as you can see, I have 80 kilonewtons as a reaction, which actually makes total sense because I was inputting 80 kilonewtons at each node on the top, so it just got transferred to the bottom, and there is not much questioning in here. Now, for the modal analysis, I will do something similar. Just quickly going to have a look in the modal parameters. So basically, I just changed the recorders. I want to record the eigenvectors for the first 3 modes that are the ones that I'm analyzing. So basically, I want to capture the deformation, the horizontal deformation, or in this case, the proportional eigenvector for A1, B1, C1, and D1 in other words, all the nodes on the top of the story. And I want to do it in degrees of freedom 1 and 2, so I can know exactly how they are moving along the horizontal plane. I'm going to do it for the first three eigen vectors, so, or eigenvalues in this case. So I will do it as you can see here. And also I'm going to increase this lambda from 2 to 3. You remember I had a 2, I'm going to do it at 3 because I'm interested in the first three different modes. In this case, since it's a 3D model, it's going to give me, instead of giving me the two modes in the same direction, it's going to give me one mode that is analog, or that is parallel to the displacement in global X, one that is parallel to the displacement in global Y, and one that corresponds to the torsion. So in order to run it, I will just simply source it up, because obviously, let me just quickly show you, I have also this small script to call both the model and the analysis at the same time. So I'm going to source it, source run modal.tcl. I run it, and then I will get my four different recorders. The first one is the one that I had in the bottom that was giving me the values of lambda, omega, and the period and the frequency. As you can see, the periods, the first period is about 0.49 seconds. The second one is 0.45, and the third one is 0.37. At this point, I don't know, or I'm not sure which ones are analog to the displacement and which one is analog to the rotation. But I can easily figure it out by looking at the vectors. So for example, if I look at the first one, I will notice, remember that I have my 4 nodes with 2 degrees of freedom. So these two first values correspond to the first degree of, sorry, to the first node on the first and second degree of freedom, to the second node, to the third node, and to the fourth node. So basically, you can see that the values, the larger values, are in the x direction, x direction, x direction, and x direction. And in the y direction, there is no really a value. It's very, very small. This is obviously negligible. So as you can see, they are exactly the same, which means that this first mode corresponds to translation in the global x direction. And that's how I know it, right? So for the second one, and this is just one way to know it, obviously. For the second one, I will open also the results, and you will notice that I have that these two, actually, they are not that, I mean, the one in the other direction is not that small, it's now quite larger. And you can see that, for example, when you analyze the first degree of freedom of the first node and the second node, they are the same. But when you go to the third zone, to the third node, it's actually the same, but with a minus sign. And the fourth node is actually the same, but with a minus sign. And this is because this is the torsional mode. And this is why also we have a large number, or a relatively large number, in the other direction. So this second mode is a torsional mode. The fact that the period of the torsional mode is larger to the period of the second translation mode, it's also related to the fact that we don't have any shear stiffness in our columns, as we are using fiber-based elements. It's just a result of the way we are modeling everything. And then I'm expecting this third eigenvector to be actually the displacement in the other direction, and effectively it is. You can see that the second degree of freedom of the nodes is all of them with the same sign, all of them going in the same direction. So I know that the third period, the first period refers to the translation in X, the third period refers to the translation in Y, and this period here refers to the torsion. Now, finally, I'm going to do also pushover analysis. I'm going to do it both in X and Y, and you can see that I generated 2 different files, one for X and one for Y. So let's start with the one in X. The one in X is going to be this file, as you can see here. I have my 4 nodes in the recorder. I only recording the first degree of freedom, because at the end I'm pushing the structure only in one direction. I don't really care about the other degrees of freedom. Same thing for the reactions, and same thing for the displacement. And I'm actually calling it reactions in X and displacement in X. Then after that, for the proportional loads, I am leaving everything very similar to the other steel moment resisting frame. I'm using the mass multiplied by the phi. In this case, it doesn't really matter because I have only one story. So my phi, that it's the eigenvector at the end, is going to be 1. So, or is the value that corresponds to the story in the eigenvector for the first mode is going to be 1 because there's only one story. So I'm using this 1. I'm multiplying it by the mass, but you can either multiply it or not. It won't change anything because it's the same value. And remember, what matters here is not the value itself, but the proportion between the values. So I'm just applying the same value in the first degree of freedom, because you can see that I have other 5 zeros here for every single one of the nodes. I am pushing the structure 10,000 steps, and my steps are 1 multiplied by 10 to the minus 5. So if I quickly check in my calculator, that means that my final displacement is going to be 10,000 multiplied by 0.00001. That means that it's 0.1 meter. In other words, I'm just pushing 10 centimeters my structure. And this is because I don't want to get any errors. Probably if I push it further, it's going to start giving me errors because I won't find convergence. For this, these are the values I'm using for the convergence tests. This depends obviously on what materials you're using, how stiff your structure is. This is just a reference, not necessarily going to be the value that you have to use. Sometimes some people might add another 0 just to be a little bit more strict in the convergence test. Some people might add more iterations. These are the iterations that you're allowing to do. I'm not interested in doing it for this model in particular, so I'm just going to leave it as it is. And just for the displacement control, I'm going to choose one of the nodes in the top, and the degree of freedom has to be in the same direction. Everything else is the same as in the steel moment resisting frame. I'm going to do the same for the pushover in Y. The only difference is that my pushover in Y, obviously, I have to consider the recorder in the second degree of freedom. I don't care the first one because I'm going to be pushing in the Y direction, in the global Y direction. My loads, they will have one of the zeros before the load and 4 zeros after, because then I want these loads to be applied on the Y or the global Y direction. Everything else is the same. I'm using the same steps, the same convergence test. The only difference here is that my node is going to be controlled on the second degree of freedom because I'm pushing in the second degree of freedom. So basically I'm changing the recorder, the loads to be applied in the other direction, and the degree of freedom in the monitoring of the displacement. So I'm also having 2 different room pushover files. They basically have the model, the gravity analysis, because I'm interested in adding the gravity loads in my model, and without removing the gravity loads, then I want to add the pushover. In the gravity analysis, you will notice that, sorry, not in this one, in this one, you will notice that I am wiping the analysis, I am removing the recorders, I am setting the time to 0, but I'm not wiping the model completely, which means that the results are still going to be there, okay? In this pushover, sorry, not here, again, it's here. I'm actually wiping everything. So when I use wipe, I'm erasing also the results. Let's say I'm just starting over. I'm just removing any kind of results. This means that my recorders are still going to be there because they are already written, but I am erasing any deformed shape or any stresses that were already inducing the structure. That's why in the gravity I didn't do it, because I want to keep the results for the next analysis, but I'm doing it in the pushover. So for the pushover, I'm going to do source run pushover in x.tcl, and then it's going to start doing the analysis. As you can see, that's the gravity, that's the pushover. And sorry, before doing that, I'm going to actually wipe everything. Oh, it's still running the analysis. So I'm getting my pushover loads. Let's give it a minute. So it has finished now. So if I go to check, for example, the reactions, in this case, the horizontal reactions, I will notice that they are here. And I can just simply copy them to my Excel file. For example, I'm going to open an Excel. And I'm going to do it only for the X direction. But it's exactly the same procedure for the Y direction. So these are my reactions. And then I'm going to do the same with my displacement. I copy, I paste it in Excel. And again, this is just a very manual way to do it. There are more optimized ways to do it. For example, with MATLAB, that is the one that I prefer. For the reactions, I'm going to sum everything. And for the displacements, I'm going to get an average, just a regular average for the values. And then I'm going to copy these values from here to here. And I'm going to paste them as values so they don't change. And I'm going to plot this versus this. So insert, and there is my plot. And you can see this is my pushover curve. I'm doing it in the weak direction of the frame, or the weak direction of the columns, and I get this capacity. And this is negative just because my reactions are recorded as negative, but obviously if you multiply by -1, it's going up, right? It doesn't mean that being below 0 is that it doesn't have the capacity or whatever. It's just the convention of my sign is taking me in this direction. Let's quickly do it in the other direction just to compare. So I'm going to do the pushover, but now I'm going to do it in Y. And you will notice that I have now a recorder for Y, reactions in Y and displacement in Y. So it's important that you change the name if you want to keep both recorders, otherwise they will be overwritten. I'm going to just close all this mess that I have open now because I don't want to get confused later. So close and close. It's still running, so I have to give it another few seconds so it reaches the result and it notifies me through this window. And there it is. It has now run. So took a little bit more, 62 seconds instead of 51. If I go, what I'm going to do here is I'm going to probably cut this because I want to put them in the same plot just to compare one direction and the other. And then I'm going to put it somewhere here just to have it there handy. And then what I'm going to do is, in a very ugly way, I'm just going to copy the reactions in another sheet just because, you know, I don't want to have a messy workspace. So this will be the sum of this plus this here. And then I'm going to open the displacement in Y. And then I will do the average of these four. Again, I will copy, this is the result here to here. I will copy it as values so it doesn't change. And then I will select these two and I will put them in the other sheet just to have them handy here. And there we go. And I'm going to do it also as values. There we go. So I'm going to drag this one here. I'm going to copy paste this curve. So my second curve that is overwritten, I will just move it over here. So we had 550 around, like the maximum. And now the second curve that we have is reaching 900 because this is in the strong direction of the columns, as you might remember. So obviously we get a larger capacity. Even though we had a larger span as well, we get a larger capacity. And then we can compare both directions of our concrete frame. one last thing that I would like to mention before finishing this video is that you have to be very careful when you run different analyses. So when you're running one analysis after the other, for example, in this case, I run the X and then I run the Y. And I told you that after the X and the Y, I was using the command wipe in order to restart everything, including the deformation that are imposed in my elements. But then also, because in this case I run, for example, the gravity, and then the gravity is not actually wiping the results or the deformation, nor the modal, as far as I can remember. Maybe it does, who knows, depending how you configure it, obviously. Let's see. So we have, yeah, no, it's not erasing, it's just wiping the analysis, but it's not wiping the results. So basically, if I go from gravity to modal and then to the pushover, then I'm running the gravity again, then I would be running two gravities, one on top of the other. And that can obviously be an issue. However, I mean, because it would cumulate the gravity load and the other gravity load, it would be adding them together. However, in my case, I just wrote, I don't know if you remember, but at the beginning of my main model, I have this command wipe, which means that every time that I call this example model 2, it's going to wipe everything. So I don't have to worry about that in particular. Just be very careful that you're not actually overwriting your old analysis with your new analysis. If you want to make sure, you can just always just wipe the entire thing after you run an analysis. Okay, so I hope this video was useful. In the next video, I'm going to do a time history analysis that is exactly the same, just I'm going to do it in both directions. And there are a few things that change in comparison with the steel moment resisting frame. So see you in the next video. Thank you very much.